Hello and welcome. Today I'll be demonstrating weld fatigue analysis of an impeller assembly. The objective is to use the seam weld capability of Ansys nCode DesignLife, as well as some model preparation work using Ansys DesignModeler and model setup using Ansys Mechanical. In order to successfully accomplish this, the user must have access to the following Ansys licenses: DesignModeler, Ansys Mechanical, Ansys nCode DesignLife Standard, and the Ansys nCode DesignLife Seam Weld add-on license. The problem statement is as follows. The impeller assembly, which is a fully welded structure, will be subjected to a repeated loading cycle going from rest at 0 RPM all the way up to full operational speed at 3600 RPM. We're going to ignore the effects of gravity for this particular case. We're also going to use the seam weld capability in Ansys nCode DesignLife to determine the fatigue life of the fillet welds. Initially, the material properties of the entire structure are hot-rolled HSLA steel. However, during the nCode seam weld analysis, nCode will leverage the fact that all carbon steels in the as-welded condition exhibit very similar fatigue behavior. nCode uses a material property called seam steel to represent this at the fillet welds and in the surrounding material. This shows the initial geometry in Ansys DesignModeler. This is a fairly simple assembly consisting of two flanged end plates. On the inside, there's also a hub to which the flange plate here is attached. And then there are 10 vanes. So these vanes are all solid, and it so happens that they're attached to the end plates using a double-sided fillet weld on each side here. You'll notice that the double-sided fillet welds are actually an integral part of the vane geometry. We're going to have to separate those as part of our modification process to allow us to do the seam weld analysis. So the intent here is to convert everything except the hub into surface bodies so we can use shell elements and leverage the seam weld capability in nCode DesignLife. The setup inside Ansys Workbench is fairly simple. We have a static structural analysis system, which we're going to use to modify the solid geometry into shell geometry. We're going to set up the loads and boundary conditions. We're going to solve the model in Ansys Mechanical. And then you can see here we've linked an nCode analysis system to our static structural system. And from here in the nCode analysis system, we'll jump into the seam weld analysis. Let's first take a look at the geometry modifications. In this quick overview section of the presentation, I can show you what we've done to the geometry to simplify it. So you can see here that we now have everything as surface bodies, except the hub is still a solid. We've actually separated the double-sided fillet welds from the vanes, and we've represented the fillet welds just as surface bodies as well. This is in keeping with the methodology and the nCode seam weld analysis. So now we're going to take this and we're going to bring this into Ansys Mechanical and set up the loads and boundary conditions. Here we have our simplified geometry brought in from DesignModeler into Ansys Mechanical. We have a multi-body part defined for all of the surface bodies. And this is going to be really great because we're going to get a conformal mesh, which is required for the nCode seam weld analysis at the fillet weld interfaces to the other bodies. Here's our mesh. You can kind of see if I zoom in here, we've got a continuous mesh, conformal mesh here across the interfaces. We've also defined our boundary condition, which is a fixed support at the hub ID here of the hole, and likewise a rotational velocity load up to 3600 RPM, also defined using this hub hole to define the axis of rotation, which is the global z-axis. We've also gone ahead and solved the model, so we have deformation vector sum results to show, as well as equivalent stress results. You can kind of see here we have stress concentrations at certain locations along the fillet weld interface. We're now going to open up nCode DesignLife and proceed with the Seam Weld analysis. I've double-clicked on the solution cell of the nCode analysis system in Workbench to open up the nCode DesignLife interface, and this is what it looks like. So here we have our results data, which has been imported from the Ansys Mechanical RST file. In addition, I had defined a name selection inside Mechanical comprised of all of the surface bodies of the fillet welds. These will be used by the Seam Weld fatigue engine inside nCode to perform the fatigue analysis, and it will assign seam steel material properties for that calculation, not the HSLA steel material properties. So it has all the information it really needs to perform the fatigue analysis. I have defined the loading condition again here, varying from 0 up to 3600 RPM. That's the loading cycle. I've solved the analysis, the Seam Weld analysis in nCode, and here are the results. And you can see results are essentially limited to elements adjacent to the weld toes of all the fillet welds. That's what the Seam Weld analysis will do. So our minimum life that we have is around 19,400 cycles based on this loading scenario. The location of minimum life occurs at this particular element here, element 67176. There are a lot of steps which have been omitted in this explanation, but this is just the overview of what the process looks like. In the next section, I'll be going through detailed step-by-step instructions for performing this analysis. The first step in the impeller assembly weld fatigue analysis is to import and modify the geometry. So here I've started Workbench session, and I've already saved it actually under this particular name. And step one is to drag and drop a static structural analysis system onto the project schematic. I'm going to right click on the geometry cell, and I'm going to import the baseline geometry. This is called impeller-geometry.xt. It's an Parasolids file. I'm going to make sure the units are US customary, and they already are. And then I'm going to right click on the geometry cell and choose Edit Geometry in DesignModeler. Next, I'm going to click on the Generate button. And here's our geometry that's been imported. I'm going to click under View and uncheck Frozen Body Transparency. And I'm going to change the units from meter to inch. So we need to make some changes to the vein geometry, and the easiest way to do that is to delete 9 out of the 10 veins, perform the operations on a single vein, and then repattern the previous veins, the other 9 veins, with the changes. So we're going to do that now. So we're going to choose from the Create menu. We're going to choose Delete, Body Delete, and we're going to choose 9 out of the 10 veins. So that's what I'm doing now. And I've got all 9. That's great. Click Apply, and then click Generate. Now we have only 1 vein remaining. The next thing we have to do is actually split the vein into 2 separate bodies. The reason being that the vein is comprised of a flat section and a curved section, and if we keep it as one body, it's going to make it difficult to do some of the other downstream operations. So we're going to create a local plane here to do slicing of this body. So I click the plane icon, and I'm going to change the type from plane to point and normal. For the base point, I'm going to go select this vertex here, click Apply, and then for the normal, I'm going to pick this edge and click Apply, and then click Generate. And here we have our plane defined now, so we'll use that to do a slicing operation. of the vane body. So under the Create menu, we're going to choose Slice by Plane. We'll pick Plane 4. Click Apply. For Slice Targets, we're going to change this from All Bodies to Selected Bodies. And then we're going to pick the vane body. Click Apply and Generate. Now our vane body has been sliced in two. The next step is to separate the fillet weld geometry from the vane body geometry. We need to do that because we need to have separate surface bodies eventually representing the fillet welds. So we're going to use multiple slice operations to do that. It's fairly simple. Under the Create drop-down menu, choose Slice. And we're going to do, instead of Slice Type, Slice by Plane, we're going to choose Slice by Surface. We're going to pick our target face, which is this face here. Apply. Change the slice targets once again from all bodies to selected bodies. Choose this vane body, the flat vane body right there. Apply. Generate. And then we're going to repeat this operation 3 more times for the underside fillet welds here. And then repeat it for the curved portion of the body. So we're going to do Create, again Slice, Slice by Surface, by this surface. Apply. By selected bodies, this body, the flat body, apply, generate. Same thing for the curved body now. So Create Slice. We're going to pick that face, apply, selected bodies, that body, apply, generate. And lastly, for the bottom fillet on the curved body, Create Slice, that face, and then this body, apply, and generate. Now we have all the fillet welds are separated from the vane bodies themselves, which is what we want. Next, we're going to mid-surface the flat and curved vane bodies. So we'll pick Tools, Mid-Surface, and we're going to pick the face pairs for the flat and curved vane bodies here. Click Apply and Generate. Now we're going to do the same thing for the curved end plates, the flanged end plates. So we're going to do Tools, Mid-Surface. And instead of doing manual now, we're going to do automatic. And we're going to change minimum threshold to 0.1344 inches, maximum threshold to 0.1346 inches. And then we're going to pick Find Face Pairs now and set that to Yes. And it's found all 8 face pairs on the flange end plates, and we'll click Generate. Next, we have to convert the fillet welds to a surface representation. For that, we're going to use Concept, Surfaces from Faces. We're going to pick all 8 faces of the fillet welds that are exposed here. Apply, and then Generate. Now I need to delete the original solid bodies for the fillet welds. We don't need those anymore, so I'm going to do that offline using a delete body operation. So I've deleted the solid bodies for the fillet welds, and you can see that only the surface representations remain. Next, we have to extend the edges of the fillet welds to the respective connecting surfaces. So this edge down to the vane body, this edge up to the flanged end plate bodies. So we have to do that for all the edges here. I'm going to do the first one, and then I'll do the remaining ones offline just to save some time. So we're going to do Tools, Surface Extension. We're going to pick that edge, and this edge of the fillet weld, this edge, and this edge. Click Apply. Up to Surface, and we're going to pick the flat vane body surface here. Better angle for that. There we go. Click Generate. You can kind of see that the surfaces have been extended. So I'm going to go ahead and continue this for the remaining edges of the fillet welds. I've now completed the remainder of the surface extension operations, so we have all our fillet welds are fully connected to their respective connecting bodies. Now I'm going to pattern the fillet welds and the vane bodies to recreate the 9 bodies we had deleted previously. So create, pattern, circular pattern. We're going to pick 1, 2, 3, 4, 5, 6 bodies. For the axis, we're going to pick the hub hole, apply, even 9 evenly spaced copies. And this should complete our geometry once I click generate, and there we go. That's all complete now. Okay, so I've gone ahead and actually created a name selection of all 40 fillet weld bodies and given it the name fillet_welds. This is going to be required for use inside the nCode Seam Weld fatigue analysis. I've also gone ahead and created a multi-body part by selecting all of the surface bodies, and you can see this in the model tree right now. We have a new part. This will ensure that we get a conformal mesh once we're inside Ansys Mechanical doing the meshing. And in fact, we're all done with Ansys DesignModeler, and so we can exit out of here and go into Ansys Mechanical. On the Workbench project schematic, you can see here I've added a nCode SN time step DesignLife analysis system, which is linked to the static structural system. We'll discuss more about nCode very shortly here. But first, let's go into Ansys Mechanical for the completion of the model setup. Now that we're in Ansys Mechanical, I can show you what has been done here, or what I've set up. So under geometry, you can see we have our multi-body part, and then the hub is still a solid geometry part as well. I've assigned materials to both of these parts that are the same, both of these groups, and that's hot rolled HSLA steel, FEE52D. This comes from the engineering data under the nCode MATML database, as I did not explicitly show that here during this recording. Details of that are contained in the accompanying PowerPoint, however. So that lays everything out how to accomplish that. In addition, I've made mesh settings for the analysis, and the element size, the global element size of around 0.2 inches. And this equates to 5 millimeter element size, which is recommended for the Seam Weld fatigue analysis in nCode. In addition, I've defined a fixed support scoped to the hole ID at the hub, and a rotational velocity magnitude of -3600 RPM also scoped, axis of rotation being the hub ID as well. So that would be rotation about the global z-axis here. Here I've gone ahead and actually solved the model ahead of time. And if we take a look at some of the deformed shape results, you can kind of see deformation where you would expect. We have kind of a leading edge of this vein here that's not very well supported by the attachment structure, so that has the maximum deformation location there. Okay, if we look at the equivalent stress results, we can kind of see, the regular pattern on the flange end plates where the fillet welds are attached. And if we zoom in to these individual veins and fillet weld groups, we can kind of see the stress distribution that we have the results for. We have some stress concentrations here on this end of the weld. The scaling on the color bar, the red lower value is set to the yield stress of this particular HSLA steel material. So these stress results, which reside in the Ansys Mechanical.rst file, are going to be brought into Ansys nCode DesignLife. and they'll be used in the fatigue analysis. I've double-clicked on the solution cell of the nCode DesignLife system to open up the nCode interface, and this is what it looks like. There are a number of operations which have to be done once you open up nCode to prepare the analysis system for a Seam Weld analysis. And this video recording will not detail those steps, but they are contained in the PowerPoint that accompanies this. So let's take a look at our model setup inside nCode DesignLife. If I click on the simulation input glyph and expand that, let's see we have representation of our model that comes in. If I right click and choose properties, you can see that input data is coming from the file.rst file from Ansys Mechanical. In addition to that, I was required to go to the Advanced tab under Properties and set import user groups from false to true. This permits any name selections defined in Ansys Mechanical to be used within nCode DesignLife. And so now let's minimize this. Now we're going to take a look at the principal model Seam Weld analysis setup inside DesignLife, and we do that by right-clicking on the Seam Weld analysis glyph and choosing Advanced Edit, then clicking Yes to this question. This will open up the Advanced Edit panel. So if I highlight the Welds Fillet category under FE Results Import, this contains information about the fillet weld analysis. So here I've previously selected the name selection from Ansys Mechanical to be the subject of the fatigue analysis, because we're doing a weld fatigue analysis. You need to make a name selection of the weld fillet geometry. So I've done that here. If I go to the Select Groups tab, you can see that I have the name selection fillet weld selected for analysis. In addition, I've set the units to be consistent with the unit system from Ansys Mechanical. Now let's go take a look at the loading setup, load cycle definition. So if I click on Load Provider Constant, I have a constant amplitude type of loading cycle defined where the stresses that were produced in the mechanical analysis are cycling between a value of 0 and a factor of 1. So what this says is essentially that the applied rotational velocity at 3600 RPM is the peak condition, and 0 RPM is the minimum condition. So we're cycling between those two states. Let's go take a look at the material setup now inside nCode. So here inside nCode DesignLife, for a seam weld analysis, all seam weld or all fillet weld geometry is going to be assigned the material called seam steel. So this is a specific material related to as welded steel structures. There's a specific set of fatigue curves that goes with this material. So if I view this data, it's going to be using this set of curves to conduct the stress life fatigue analysis. All the other material data that's assigned to the other weld bodies, that would be the flange end plates, the vane bodies themselves, they're essentially ignored because only around the fillet welds themselves will the fatigue analysis be conducted. We can now go look at the general setup for what's called the Seam Weld engine, the solver. So most of these or all of these settings we're going to leave alone. The defaults are usually very good. One note is that we're using absolute maximum principal stresses in the fatigue calculation themselves, and we're using a mean stress correction called FKM. So if I now click OK, we come back to the main interface, and if I click this play button up at the very top, this will actually perform the solution. and it's very quick because it's only doing the elements adjacent to the fillet weld toes. So here is the resulting set of data. So here I'm looking at life, fatigue life. In nCode terminology, that's also called repeats, as in repeats of a given loading cycle. You can see that at the bottom of the contour panel, they provide a minimum fatigue life and the location at which it occurs. This happens to occur at element 67176, and the value is about 19,400 cycles until fatigue failure. You'll notice that the displayed contours only appear at elements adjacent to the weld toes of the fillet welds. Again, so the seam weld fatigue analysis is specific to these locations. Should you want to perform a fatigue analysis on the rest of the structure and not consider the seam welds in particular, then that would be a separate analysis, which is actually a little bit easier than this one. If we would like to review the location at which the maximum, or I should say the minimum fatigue life occurs, we can use what's called the Hotspot List. So if I click on this icon, this lists the lowest fatigue life locations in the model. And if I click on element 67176, it provides a label, and that will help us kind of see where that location is. So if I rotate around here, you can kind of see that the minimum life actually occurs at the end of this particular fillet weld on the inside location. So that's an overview of seam weld analysis inside nCode DesignLife. Thank you very much for watching. Please be sure to take a look at the accompanying PowerPoint, which provides more detailed information. And thank you very much.